Hi everybody, this is Professor Mankowski. In this video, we're going to talk about Chapter 8, Section 8-3. Now, we found out so far if we're going to run a hypothesis test, we need a lot of information to get the hypothesis test off the ground. We have to know a lot of information about the population that we're working with, and we have to know a lot of information about the sample that we're drawing from the population. So somebody needs to tell us the population average, the mu, the sample size n, the sample average x bar, the sigma, population standard deviation, and our alpha level. So it's a lot of information to have to juggle around, and it might feel like you're juggling with fire too. But what's important is in the midst of all those different symbols, there's one of them that's going to turn out to be unrealistic to assume we're going to know it. So what do you think is the culprit? Which number do you think we're never going to have in real life? The answer is going to be the population standard deviation, because most of the time we won't know anything about the population. So why do we keep assuming we're going to have sigma to work with? And that puts us in kind of a funny spot, because now we need to figure out how do you run a hypothesis test if you're missing one of your key pieces of information. Now, in Chapter 7, we had a similar issue when we were looking to study confidence intervals, and we needed a sigma for our formula. And at one point we realized, what if we don't know sigma? What would we do? And the answer was we had to substitute the sample standard deviation for sigma, because there was literally nothing else to use. So when we do that, the same thing happens in hypothesis testing in Chapter 8. We're going to get bumped to the t-distribution, and the good news is the t-distribution is much easier to work with than the z-distribution. And the big benefit of using the t-distribution is it's going to make the critical regions much smaller. And that's exactly what we want, because we don't have very good information that we're basing the hypothesis test on. Remember, we don't know sigma, and we're basing our hypothesis test on an estimate of sigma. That's what the sample standard deviation is. So if we're going to reject a null hypothesis, we have to have a sample average that's very, very far away from the population average to do a rejection and be comfortable in those circumstances. That's why the critical regions are getting smaller, and we'll see an example of this work into the hypothesis test later on in the video. Okay, so what are some main differences between hypothesis testing with the z-test and with a t-test? First is going to be critical values. When we do the hypothesis test, one of our big differences is our critical values will come from the t-tables, and in the prior videos that we were doing, critical values came from the z-tables. So obviously we're switching the spot where we get the critical values. Now, we're also going to be using, instead of the z formula, a t formula. And our big difference in the t formula, it looks just the same as the z formula, except sigma has swapped out with the s, and now we call it t instead of z. The majority of the hypothesis test is still going to be the same way that we've performed it earlier, except with the difference of critical values and our difference of s inside our formula instead of sigma. So let's talk about, before we get into the hypothesis test, how you actually get those critical values from the table. Now, there's a couple of things that we need if we're going to get our critical values. For on t-distribution, we need to know our degrees of freedom, and we also need to know our alpha level. So once we know those two things, let's go ahead and let's work 2 or 3 cases where we're going to see how you would actually look up your critical values if you had reported exactly that information. So our first case is going to be, we're doing a hypothesis test, and what we know is that there's a 0.05 level of significance, or alpha. We have 10 degrees of freedom. So we're going to pull out our t-tables, and your PDF packet, they're going to be on page 3. It's just one table. Now, when we look to the lower left, the upper left, we see a column for degrees of freedom. So we're going to go ahead, we're going to drop down degrees of freedom, and we're going to identify the row for 10, which corresponds to 10 degrees of freedom. At the top, we have 3 choices of rows to navigate through: confidence intervals, one tail, and two tail. We're going to be using the row for one tail because we only have one tail test that we're working. It's a left tail. So I'm going to find the alpha up there that equals my number, 0.05. And our intercept is going to be 1.812, where the column intercepts the row. And here's where you need to avoid a really big mistake. Remember, when they invented the t-distribution table, they knew that the whole table was symmetrical, so they decided to only list half of the values. They figured we're only going to list the positive values. And we have to remember, if you're doing a left tail test, you need to put a negative in front of that critical value. If you forget to do it, it's going to get you all mixed up when you go to evaluate your decision rule and make your conclusion, because nothing's going to make any sense. Everything's going to be on the wrong side of the curve. Okay, so critical value, negative 1.812. Let's do another case. So case 2, we're looking at a right tail test, alpha equals 0.10 and 5 degrees of freedom. So we're going to start the same way. We're going to look at our degrees of freedom column. We're going to drop down, identify the row for 5 degrees of freedom. We're going to use up at the top our row again for one tail, and we're going to identify 0.10 because that's our alpha level. Our intercept is going to be at 1.476, and that's going to be our critical value. It'll go on the right side of the average on our curve. And let's do one more. The only thing we haven't done yet is a two-tail case. So we have alpha 0.10 with 5 degrees of freedom. I'm using my degrees of freedom column. I'm underlining again that row for 5 degrees of freedom. At the top, this time we're going to use the row for two tails. And I'm going to find my column matching my 10%. And when I intercept my column with my row, I have two critical values, plus 2.015 and minus 2.05. So now we've seen how to find the critical values. Let's go ahead and let's work a full-blown hypothesis test. And this one is coming from question 8 in section 8-3. So go ahead, pause the video for a few minutes to read through the question. They're telling us in here that if you commute to work, it's going to take you on average 25.4 minutes to get to your job. And there's this Chamber of Commerce executive, they think in their city the commute time is less, and they want to go out and try to prove that somehow. Now, if they're correct, if the commuting time is really less, that's really good news for your Chamber of Commerce official, because it's their job to grow the town, to attract business to it. So if something like this is true, that their commuting time is less, that's really useful information for them to promote their town with. So they went ahead, and it looks like they did a random sample of 25 commuters. The average commute time was 22.1 minutes. And when we look at 22.1 minutes, we might say, heck, that's obviously less than 25.4 minutes, so can we just stop here? No, we wish we could. What we have to do is find out, is 22.1 minutes significantly less than 25.4 minutes? If it's significantly less, then we have enough information to reject a null hypothesis. But if it turns out it's not significantly less, we can't reject a null hypothesis, because it means that our sample average is within sampling error of the population average. Okay, so what's the most important thing that we have to check for in the question before we even start doing anything, before we start doing work and formulas? What we need to think about is we're doing a test for a population average right now, and at this stage we know two different tests. We know a t-test and a z-test. So we have to start by thinking, which test are we going to do? And this means we have to locate the standard deviation, and we have to figure out where the standard deviation came from. If it's from a sample, t-test. If it's from a population, z-test. So it looks like our standard deviation is mentioned in the context of the information. That's when they're telling us about what happens to the sample. So it's safe to say we're probably going to end up using a t-test, because the standard deviation of 5.3 is clearly in the information they're giving us from the sample. And notice they're being kind of tricky. They don't come out and say 5.3 minutes is our sample standard deviation. We have to infer that from the words, and that's what kind of makes this a little bit tricky. So what we're going to do now is we're going to start to write down all the numbers that they gave us inside the question. And since we were able to figure out the standard deviation of 5.3 is a sample standard deviation, we're going to go ahead and label 5.3 our S value. We identified 25 commuters was in our sample, so that's going to be useful. 22.1 was also our sample average, because 22.1 is also mentioned in the context of what's happening in the sample. So we're going to label 22.1 our X bar. Our 25 we can label as our sample size N. And 25.4 is actually going to turn out to be the mu because it's the only average left in the question, and it's certainly not connected to the information of what's happening with the sample of 25 commuters. So it must be mu. We know our alpha level would be 0.10 because they mentioned that in the last sentence. And the only number that we have left to worry about is the 15. So where does the 15 go to? Nothing is the answer. Now, how did we know that it doesn't go to anything? And the answer is, when they're mentioning 15 large cities, the only thing that could possibly be is some kind of information about a sample. But since we already identified everything we need to know about the sample, that means that it's probably there just as information they're presenting, but it's not really going to get used in the formula or the calculations. So now we have everything we need to think of to start creating our null and our alternative hypothesis. The null hypothesis will follow the same pattern it always has. Mu equals our population average. Now, for the alternative hypothesis, we know that our keywords are less. The Chamber of Commerce executive thinks that the commuting time is going to be less, so we're going to engineer a left tail test. And now we're going to get ready for our critical values. Remember, we're back to the t-tables for the critical values, and our critical value will be negative 1.318. So I'm going to go ahead and shade that in, mark that as my critical region. And this is telling me that when I eventually look at my sample average, I can only reject the population average if that X bar, my sample average, fell 1.318 or more standard deviations below the population average. And that's in place because when we started the question, they gave us an alpha level of 0.10. And that means we can only reject the null hypothesis if we end up getting a sample average that we didn't even have a 10% chance of getting. So how do you know if you had less than a 10% chance of getting the sample average you did? Well, critical value says the sample average would have to be identified as being more than 1.318 standard deviations below the mean. So let's go ahead, let's start to think of our T formula. We're going to fill in all of our parts here, our information, and our test value is going to come out to be negative 3.11. So now I'm going to go ahead, I'm going to take that test value, I'm going to compare it to the curve. And I'm noticing it looks like it fell in our critical region. So now it's time to apply that decision rule. If the test value falls in a critical region, reject the null hypothesis. So we're going to conclude and make it official by saying it appears the commuting time in this city is below 25.4 minutes. So if this information was presented to our executive, would it make them feel really happy or really sad? And the answer is it's going to make them feel really happy because it gives them more information to promote the city with. Let's do another practice exercise. So pause the video if you need to for a couple minutes to read through the question. I'm going to move a photograph out of the way here. Okay, so one of the first things that we notice is they were kind of mean to us in the question. They gave us a sample data set to work with. They can also be really helpful for our advantage though, and here's why. They're talking about how the average person has worked 9.2 jobs, and we need to go and find out, is that the right number or not? So somebody has taken a sample of 8 workers, and we have to use that sample to mine out all of the information we need for the hypothesis test. So here's the good news. If you're doing a sample data set, it's almost always the case that you're going to be calculating the sample standard deviation yourself. So that means if we're calculating a sample standard deviation, it must be a t-distribution test. Okay. So as we're thinking about how we're going to get the hypothesis test off the ground, the first thing that we really have to do is take care of the heavy lifting. Let's get that sample variance calculated because we're going to need that anyway. And as we're looking at the formula, it looks like it's saying that we have to take each x value and subtract it from the average. So that means we're going to need the sample average. And that calculates out to be 8.25. So what I'm going to do now is I'm going to start to get ready to take the each x value and subtract it from the sample average. So I'm going to start by listing down all of my x values vertically. Right next to that, to make the subtraction easier, I'm going to go ahead, I'm going to list my sample average row by row. And I'm going to make another column to take each value in the column on the left, subtract it from the one in the column on the right. And that's going to be my differences. Everything in purple corresponds to the part of the formula that I've circled in purple. And now it's telling me I have to go to that whole entire column. I need to square up all the values there. So I'm going to make a fourth and final column where I'm going to take everything that I had in the preceding column. I'm going to square it. And these are all my values I get when I do that. I'm going to circle the parts that are matching the numbers in the circle the numbers that are matching the parts of the formula. And the last thing in the formula I need to do is sum up that last column. So I'm going to put in a summation sign. I'm going to add up all those numbers, move that to the upper left, and my sum is 179.5. So the formula is saying I need to take that 179.5, and now I've got to come in and divide it by 1 less than the total number of observations. That's going to be 7. And that gets me 25.64. Am I done yet? No. I've calculated the sample variance, but what I need for the formula is my sample standard deviation. So I have to do one more step. I need the square root of 25.64, and that's going to give me 5.1. Okay, so all that work we did, and we didn't even start the hypothesis test yet. But now we have all the information that we need so we can start rolling on the null and the alternative hypothesis. We're going to go ahead, we're going to list all of our information in summary form at the top of the screen. And they've asked us in the question to find out, is the population average different than 9.2? So it's going to be code for a two-tailed test. Because even though 8.25, our sample average, is less than 9.2, don't go ahead and rush in and say that must be a left-tailed test. That's the number one mistake students make on the two-tailed test, is they don't look in the keywords for the designation on H1. They just compare X bar to mu, and this is exactly where it would get you in trouble. So because they use the phrasing, is the average 9.2, they don't know if it's supposed to be higher or lower. It's kind of like pretend we don't know what the sample is yet. So HO is going to get written in as mu equals 9.2. The H1 is going to be not equal to 9.2 because we're going to do a two-tailed test. Our critical values are going to end up being a plus and minus 2.365. So if I want to reject the null hypothesis, my sample average must be 2.365 standard deviations above or below the population average. I'm going to shade in those critical regions. Now we're going to start to calculate out our t-value. And I need to move something on the screen so I can see all this. Oops. Bring back everything we had. Okay. So our value is negative 5.31. When we compare that with our curve, it's definitely not falling in the critical region. It's actually in the acceptance zone of the curve, which means that obviously our sample average was different than the population average, but the difference was insignificant. It's insignificant if our test value lands in the acceptance region. So if it's insignificant, that means the difference was merely due to sampling error. So we're going to go ahead and write in that we're accepting the null hypothesis. And for our summary step, we're going to say it appears that the average number of jobs worked is still 9.2. Okay, let's talk about one other thing that's really important here. We mentioned it in the beginning. We were talking about how when we do a t-test, the important thing that it's doing for us is it's shrinking the critical regions. Let's see how that's actually going to work and play here. And I got to rearrange part of the screen again. Okay. So on the left, we have the critical values exactly as we were just working with them in the question. And on the right, we're going to go ahead and we're going to set up a curve with critical values as if we actually knew the population standard deviation. So if we pretended we knew that, that would put us back on the Z curve. And if we're using an alpha of 0.05, our critical values will be plus and minus 1.96. And notice how those critical values are pushed more into the center of the curve. And that is exactly what we want. Think about the flip side. When we're on the T curve, the critical values are further away. So it makes it harder to land in the critical region, and that's what we want. because we're relying on a small sample to do our hypothesis test. So if we're going to do a rejection, we really want a sample average that's vastly different from the population average, so we don't have any doubts when we're rejecting the null hypothesis. Now, it just happened to be the case that we ended up accepting the null hypothesis, but it's still really important to see how the critical regions are changing in position from the z-curve to a t-curve. Now, we're going to talk about one additional thing here, and what that has to do with is if you were doing a hypothesis test, what would happen if you ended up with a really biased sample? Like you just had a crappy sample, it was biased. Could that actually end up making you do the wrong decision on the hypothesis test? Like, could it make you do a rejection when you should have done an acceptance, or vice versa? So what that has to do with is something called type 1 and type 2 error. And where we're going to start is, we could say that when we finish a hypothesis test, there's only two real possibilities. Either we reject HO or we accept it. Now, in real life, there's also two possibilities. Either HO is really true or HO is really wrong. So we kind of get a matrix out of this. And if it turns out that we rejected the null hypothesis, but in real life, it was really wrong, then that's good, because it means statistics did exactly what it was supposed to do. It gave us the right answer. But if it turns out that we rejected the null hypothesis and in real life it was really true, that's really bad, because that means statistics did not do what it was supposed to do. We probably had a biased sample and we did not realize it. When that happens, that's called a type 1 error. And what's really important is, we'll never actually be able to prove if we made a type 1 error. We just acknowledge that it might happen. Let's check out the bottom side. What if HO was accepted and in real life it's true? Good, right? Because that means statistics did its job. But what if we accepted the HO and in real life it was the wrong hypothesis? It really wasn't true. Well, that's really bad also. And if that happens, it's called a type 2 error. And again, we can't be sure if we ever made a type 2 error or not, but we can acknowledge that it might happen when we do the hypothesis test. The last thing that we need to know is the chance of a type 1 error happening would be exactly equal to our alpha level. And let's take a quick look at why. We go back to the question that we were working with when we were talking about the commute time to work. Remember, when we take our sample, we're assuming that the null hypothesis is true until we get enough information to show it isn't. So we start a hypothesis test, and in the center of our curve, we would be thinking that 25.4 is in the center, because we believe the null that mu is equal to 25.4. It's going to be the case that if we shade 10% of our curve area like we've done, and the null hypothesis is really true, it means that exactly 10% of the time we're going to have a sample average that lands in the critical region. So the translation is, there's a 10% chance that we're going to end up rejecting the null hypothesis by mistake. And that's exactly why the chance of a type 1 error is exactly equal to our alpha level.